Hey everyone, this is David with Streaming Relativity, home of the AstroDNA Observatory. Today we're going to talk about workflow for deploying the iOptron CEM120 to a permanent pier, in my case to my observatory. This is a follow-up to the unboxing and initial testing video that I published earlier this week. And if you're interested in the CEM120 or plan to purchase any mount for that matter, use the link in the description below and check that video out as well. Finally, if you are an amateur astronomer and you're into astrophotography, you might as well subscribe to the channel. I have a ton of content to publish, and I hope people will find the content interesting and helpful. Okay, with that, you notice that Nina is on screen in the background, and I figured this would be a really cool teaser for the video. What you're looking at is the very last sub that was captured in the first light sequence using the CEM120 mount. This sub exposure is the last of a 4-hour long series, so let's not focus on the image right now, but this happens to be a 120-second exposure of NGC 1975. That's the Running Man Nebula in Orion. And I used my Celestron C8 with an ASI 1600 monochrome pro camera. I was at unity gain, and this happens to be with a luminance filter. This was the last sub captured. But rather than that, why don't we focus on the PhD2 guiding log, which I was really happy this morning when I woke up and I took a peek at it, because really relatively flat. The total RMS is about 0.72 arc seconds across the 4-hour period. There's a couple of gremlins here that I want to take a look at. I'm not sure what those are, but I'll inspect the logs in more detail. But given that this is simply a deployment of the mount, I did a polar alignment and used PhD's guiding assistant just to quickly get it calibrated, and ran first light with this. I'm actually really happy with 0.72 arc seconds of total RMS. Now I know with some tuning we'll get this really dialed in, but that's a separate journey. So what I'd like to do is go ahead and talk about the deployment workflow that I use to actually get to this point. Okay, let's start with the goal of the workflow, which is to get the mount installed on a permanent pier or a tri-pier, and then conduct a successful first light sequence with a mounted OTA and an image train. I divided this workflow into 5 distinct steps. First is planning and preparation. There's nothing worse than being in the middle of the deployment and not having a tool or a part that you need, or having the wrong part because you simply didn't measure something properly, like a bore diameter or a length of cable, or perhaps you got the pier orientation wrong given the azimuth range of the CEM120. So please prepare by planning well in advance. Second, pier adaptation and mounting. This is where we attach the mount to the pier, and then we balance our rig. And this may require pier adaptations. In fact, in my case, it did. So I'll go over what my issue was and what I did to ensure that the secured mount was in the proper orientation needed for precise polar alignment. Third, mount control. We are going to establish mount control from our observatory computer. And I recognize everyone has their own system for controlling their rigs. I happen to use Nina installed on a mini PC, which is fairly common. Regardless of the control system that you use, you do have options for connecting that control system to the mount. Fourth, power and data distribution. Beyond controlling the mount, you'll need to connect cameras and imaging accessories to your control system. So I'll share how I leverage the cable management system of the CEM120 for connecting my astrophotography components. Finally, first light. We'll cover what the minimal configuration that is needed to execute a successful first light sequence with the mount. And of course, this is where all that hard work and investment actually pays off. Before we go into the workflow, I have one recommendation, and that's minimize the unknowns going into this process. And what I mean by that is use an OTA and imaging setup that has predictable outcomes. In other words, if you purchase the CEM120 for a brand new, say, a 150 millimeter refractor, but you haven't tested that refractor yet, you haven't set up its imaging train, don't attempt to do both things at once. That's going to be very difficult. Stay focused on deploying this mount and getting a successful first light by using a rig that has predictable behavior. All right, with that, let's move on. Okay, the level of planning and prep that you need to do is a function of your target deployment. And for the purposes of this video, I'm going to assume that you are deploying the CEM120 on either an iOptron permanent pier or the iOptron tri-pier, or any pier that you have adapted to accept the mounting bolt pattern of the CEM120. And that means that the pattern is correct and the thread size matches the mounting screws that are shipped with the mount. If your pier doesn't support that requirement, you're going to need an appropriate pier adapter plate, which you can probably find online. Or if you're ambitious enough and you have the tools, you can machine your own. Okay, with that said, let's talk about the planning steps here. You're going to need to do a bunch of measurements, and you should do these in advance. And in my case, here are the things that I had to measure. First, the angular rotation of the pier to achieve the proper northern orientation of the mount, and that would be when the mount is in its zero position. And then I needed to do, because I'm deploying to a pier inside of an observatory, I needed to calculate dome and mount geometry values that are used by NINA and other programs to synchronize the slewing of the dome with the slewing of the mount itself. So there's an algorithm that's used by software that ensures that the telescope is pointing out through the center of the dome aperture or shutter, once it acquires its target. All of this is dependent upon offsets of the mount center from the dome center in 3 dimensions. So you need the north-south offset, the east-west offset, and the up and down offset. And the mount center is, for the CEM120, and all equatorial mounts for that matter, is the intersection of the RA and the deck axis. So think of the point at which those two axes intersect. That is what we consider to be the mount center. So the telescope north-south position is the offset of the mount center, that intersection point, from the dome center. Telescope east-west position offset, that's the offset of the mount center from the dome center. And the telescope position up-down is the offset of the mount center from the dome center. Fourth measurement is the GEM access length, which is simply the distance to the center of your OTA tube from the mount center. And when I make that measurement, I also consider the fact that I use a guide scope as opposed to an off-axis guider. So I usually have a slightly longer offset beyond the center of the OTA so that the pointing considers the guide scope as well. So other measurements, lengths for the USB 2.0 and USB 3.0 cables that you plan to use for connecting your observatory computer. If you are using the cable management system, you're going to have multiple USB 2.0 cables and a USB 3 cable, and the same applies for iPolar. In my case, my measurements, my mini computer is located 15 foot away from the from the mount, the point at which they would plug into the mount. That's kind of pushing it for USB 2.0. and frankly for USB 3.0 distances. But I did secure, that is the measurement, and I did secure cables for that, and we'll talk a little bit later about whether or not they worked. If you're going to use a network connection to control your mount, you'll need to understand the length between your mount connection point and wherever your local network switch is. So supplies. If you are doing pure adaptation or changing pure orientation, make sure you have your bolts, your lock washers, your nuts, and they have to be of the right size and quantity for your application. You will need the CEM120 accessory box and all of its contents. You need the hand controller. You'll need a CR2032 3-volt battery for the hand controller. You'll need the power brick supplied by iOptron. Optionally, you'll want an additional 12-volt up to a 10-amp power supply for the cable management system input panel. You'll need your cables, your USB 2.0, 3.0, and Ethernet cables according to the length that you've measured. I wound up employing an actively powered USB 2.0 hub. You might as well have one of those ready to go. Have a bunch of different short-length USB cables, 2.0 and 3.0 cables for connecting your imaging cameras and accessories to the saddle of the CEM120. Identify the rig that you intend to use in this workflow. I decided on my C8, my Celestron C8 with my ASI 1600 monochrome pro camera. Its outcomes are very predictable for me. So if the CEM120 is set up and guiding well at the end of this, I know what to expect in terms of my subs. You'll need, at least you might want a roll of Velcro tape, and some twist ties, and then certainly have a notebook and a pen handy for any notes that you might need to take along the way. In terms of tools, probably the number one tool here is a partner. This is very heavy, and I needed my father's help along the way. So if you can, have a buddy help you out here. You'll need a ladder or a sturdy step stool for both the mount and the telescope placement. And of course, the taller your pier, the higher it is, the more important that this is. Have a small level to ensure that the pier top plate is level before you mount the mount. Have a compass to ensure that the orientation that you will be setting your pier in allows for true north along one of its edges. And remember, you only have about 10 degrees of azimuth adjustment with the CEM120. Tape measure is necessary for all the measurements we talked about earlier. Small Phillips screwdriver for removing the hand controller cover and installing the battery. A pair of scissors for cutting the Velcro tape, and then the hex wrench set provided by iOptron. That's that brass set for tightening the mount screws and the altitude locking bolts. Again, depending on whether or not you're doing any kind of adaptations to your pier, you might need a couple of crescent wrenches as well. Finally, in terms of a control system and software, you should have an observatory computer to connect to, or whatever system that you intend to use, with sufficient USB ports for all the connections that you intend to take advantage of from the CEM120. Astrophotography software to handle your sequences, because we are going to do a first light. I happen to use Nina. And then I use software for polar alignment. I use SharpCap. There are other alternatives out there, including iOptron has their own iPolar solution. So that's the planning and the prep work. So let's move on to getting the mount and the optical tube assembly up and balanced. I've broken this step of the workflow into two parts. First, I'll address pier adaptations that I needed to make to support the CEM120. And then the second part, I'll discuss physically securing the mount to the pier and then the OTA to the mount, including balancing. Feel free to skip adaptations if you're not interested, but if you have or plan to install a permanent pier, it may be worth a couple of minutes of your time to see what I had to do. In terms of adaptations, I had to actually machine a new Pier base plate that allows me to rotate my Pier 45 degrees counterclockwise from its original deployed position. My prior mount, which was an iOptron CEM120, it employed a Pier adapter plate, which required the pier orientation with north pointing over the corner of the pier top plate. The CEM120 natively mates to the pier top plate, and it requires no adapter, and north orientation is actually perpendicular to the side of the pier top plate. So here's the new hole pattern with 8 half-inch bores featuring 45-degree angular separation, and that is my new base plate. And I used a drill press and a half-inch carbide bit, a few drops of oil to machine the 16-inch diameter quarter-inch steel base plate, and that now allows me to rotate my pier in either direction to support either mount, the GEM45 or the CEM120.
Right. Why do you want this recorded?
Because I'm going to do a blog post on it.
You're gonna what?
I'm going to blog it.
Go slow. You don't want to hear that noise.
My dad and I obviously have had a lot of fun with this observatory project over the years. Why don't we take a peek at the adapted pier after it was reinstalled in my observatory? I'm going to speak just for a moment on this, on the pier that is here. This is a concrete pier. It's 16-inch diameter concrete, isolated from the floor, as you can see. The base goes down about 3.5 foot, 4 foot, and it widens. So the concrete footing is pretty solid. And protruding from the concrete are 4 bolts that are J-bolts, they're half-inch J-bolts. And I use a 16-inch diameter quarter-inch steel plate to set as a base for the iOptron pier. This is the, I guess they're 3 foot pier, or I believe it's 3 foot. At any rate, in addition, I showed that plate machining work. There are holes that allow for the iOptron pier to be fastened to the top of this plate, which has been leveled. So this is how I get a nice sturdy pier, stable pier in the observatory. With our pier properly oriented and secured to the pier footing, we can move to the mounting of the CEM120. Be sure that the gear and axes levers for both the deck and the RA are in the proper transport or install position. And again, that's where the gear levers are unlocked and the axes levers are locked. Also, do not transport or install the mount with the counterweight shaft screwed in. This is just going to add weight, bulkiness, and risk to damaging your CEM120. Put the shaft in after you have the mount secured. So we've got the mount secured, and really securing the mount is a very straightforward process for cases where you are using an iOptron Pier product. So the top plate of the Pier product mates natively with the base plate of the mount, and you can hand tighten on all 4 corners, and then from there, once you are hand tight on all 4 corners, You can then use the hex wrench that's available to really tighten this down. At this point, I would go ahead and adjust the mount for latitude of your location before going any further. And of course, when you first set the altitude, it's going to be rough, meaning that you'll have to dial this in later on in the workflow through a polar alignment. But to do the rough adjustment, you're still going to need to loosen the altitude locking screws on either side of the CEM120 about a quarter of a turn or so. You simply want to allow for smooth operation of that altitude adjustment knob. Now, for a rough setting, you should obviously know your latitude. And in my case, my latitude is 41 degrees and about 19 minutes. So I roughly set it to 41 and a little bit past that on the dial. And then after polar aligning, it wound up settling in at around 41 degrees and 30 minutes according to the dial. Now, first of all, that's not horrible given the inherent lack of precision of any set of dials and markings on the mount. It's actually pretty good. However, if you want it to be perfect, you can loosen the set screws on that dial and then adjust the dial to your exact minute for, in my case, let's call it 19 minutes. And then replace that dial and secure it again with the set screws. I honestly don't feel compelled to do that. I'm more concerned about having an accurate polar alignment regardless of what those settings say. But it is good to know that the precision is pretty good out of the box for the CEM120. Okay, mounting the OTA to the saddle. Your options are a Los Monde D dovetail plate, which you can see this is the Celestron C8 with the Celestron plate itself, and it's a clean fit. I've heard people on the forums report that the precision of the saddle was questionable, but I didn't find that to be the case. I found it to be an exact fit. So the real trick was having to slide the OTA in as opposed to dropping it in. I covered that in an earlier video. A little bit of experience with this OTA. I knew that I wanted to slide it from the rear towards the front. I just feel more comfortable navigating the saddle with my image train and all of the accessories behind me, and not interfering with any travel. Path of travel here. So at any rate, there are, as we talked about earlier, there are 3 knobs to apply tension to the dovetail plate of your OTA, and getting it into position and then securing these knobs hand tight first and not letting go of the rear of the OTA under any circumstances is a bit of a trick, and having somebody help you is always good. Once the OTA has been placed into the saddle, it is time to put the counterweight in place. As it turns out, with the C8, the position of the counterweight is roughly centered on the shaft. I often read that it is recommended that you balance the deck axes before you balance the RA axes. And honestly, I generally balance the RA axes first, and I know that goes against some documentation, and there's probably good reason for the documentation. But when I balance my deck axes, I usually do that with the RA axis rotated 90 degrees from its home position. And I like to do that knowing that there's basic balance already established on the RA axis. So I'm going to show you I'll demonstrate the balance on the RA axis first. I balance in iterations just to make sure that I'm safe. My first step is to be safe. and then I get into fine tuning. So at any rate, to release, to allow the mount to rotate over across its RA axis, at this point we want to rotate this way, meaning we want the scope to be balanced. The total mass of the OTA, total mass of the OTA needs to be balanced by the counterweight and its position. I'll talk about the counterweight in a moment. What I don't like is that I'm limited as to how far up the counterweight can go before it actually becomes the pier top becomes an obstruction. And I know there are some alternatives, weight designs for that I'm going to look into. I much prefer my counterweights to be as close to the center of rotation, the center of the mount as possible. But in this case, one of the 22-pound counterweights just past midway on the countershaft. If I go ahead and unlock the gear, the RA gear, you can tell there's not even a moment of inertia or a rotation here. So just giving you a sense for how well balanced this mount and how smooth this mount is. So a balanced OTA basically means that at any point when we rotate it to any position, that it's going to hold its position without further movement. And you can see here there's a little bit of swing, which means that I'm probably counterweight heavy. But let's check that. Let's check that from the other side and see whether or not we're counterweight heavy. I let go, and then again we can see how it is swinging, swinging again in a counterclockwise position. And there we go. We have a little bit of a pull. It feels to me like in the east to west direction. We'll try that again from a higher spot. Seems okay here. Once you get I start to make this turn, little bit of a pull, and so we're probably going to want to perfect that. Now let's just test it over here. And in this case, we have a little bit of a pull now from the west to east direction. So I'm going to go with the theory that my counterweight I'm a little counterweight heavy here. Now, it's likely that in this case I'm counterweight heavy because I had a dew shield on when I originally balanced this. So I'm experiencing some serious problems with the dew shield and the dew ring. So I'm going to, just for purposes of this video, I'll adjust the counterweight now to demonstrate achieving balance in the RA axes without the dew shield. So that's what we're going to do. With a relatively small adjustment, shifting the counterweight, I would say somewhere in the neighborhood of 1/3 of an inch towards the center of the mount, we now have really good balance in any position that I place the counterweight. So the counterweight shaft. So let's try it from this position. Will it hold? It does. Let's try it in this position. Again, just try a few different positions. It's perfect. So we have I would say we have something near a perfect balance at this point. There's not even a small hint of movement. And so at this point we are balanced in RA. So I'm going to go ahead and lock the RA axes at about a 90-degree turn. And so we're now engaged at 90 degrees, and that's going to allow me to move over to the deck axes. And this is pardon the videoing of this. And it's going to allow me to do some balancing of the deck axes a little bit easier. So the first thing I'm going to do is I'm going to release the lock on the deck. And again, I'm doing this with the knowledge that I'm already balanced, or quite balanced. Notice no movement on the scope when I release the gear. So I am going to now manually move this to a roughly horizontal position to see if it holds balance. And it's a little back heavy. I mean, very slightly back heavy. Very difficult for me to demonstrate that, but it moved ever so slightly. I'm going to adjust. Again, I'll adjust. This time I'll go into a position. So she's back heavy. Okay, let me try from top to bottom. Feels pretty good here, vertical, and you would expect there's very little. But once we get to here, we're still okay. Let's go here. We're fine. Actually, it looks pretty good. And if I go practically upside down, and we are fine. So we're actually quite balanced in the deck and the deck axes. The best way to tell is actually to be, if you're vertical, I should say horizontal, and you don't have any movement of your OTA, and she holds position well, then I think it's safe to say that we're in good shape. So I'm going to go ahead and simply lock my deck, and now everything is locked and engaged. I am powered on at the moment, and what I'm going to do is tell it to search for its home position, and to search for its zero position, and she'll adjust. Everything will adjust. It's a nice feature of iOptron to have a search for zero position. I like it because it's driven by sensors inside the mount housings, and it's a reliable position. So I actually polar align against the built-in zero position, and I recommend you do the same, unless, of course, your zero position is so bad that you need to adjust it, which you can do with the controller. And that's exactly what's being asked right now. Would I like to calibrate zero? And the answer is no. So I hit back. And at this point, we are at the zero position on the mount. We have balanced RA and deck axes. And this mount is ready for precise polar alignment. Okay, so my observatory system is a mini PC mounted on one of the side walls of my observatory structure. And I have a monitor and my keyboard and mouse directly connected to that via USB. I also have my switch, my network switch, which is mounted just below the mini PC. And the distance from my equipment to the base of my mount, I should say my mount control panel and roughly the input panel, is roughly 15 feet. So, or 5 meters, which is right at the limits of USB 2 and even past the limits of USB 3. So let me go over how I connect everything. So this is my spaghetti setup. Everybody has their own, but it's truly not that bad. I'm going to address USB and LAN cables first, because this is data. This is the data that I have being transferred to and from the mount and my control system. The LAN speaks for itself. It's about 15 foot long. I opted for a LAN connection as opposed to a USB connection to the mount control board. I have a switch. I can take full advantage of it. iOptron's commander will speak over will obviously speak over Ethernet, and heck, why not isolate commands to the mount from data flow back to the computer? Speaking of data flow, I am running both USB 2.0 and USB 3.0 cables to the cable management system, and I am successfully running, oddly enough, a 5 meter or 15-foot USB 3 cable back to my computer, but I was unable to successfully have a 15-foot USB 2.0 cable run back to my computer. I was a little disappointed in that. But that is not a function of the mount or a problem with the mount. Arguably, it's not a problem with the mount. Perhaps their USB electronics are a little bit on the commodity side, but really 15 foot is a push for USB. So rather, I opted to have a powered USB hub mounted on the pier itself. And surprisingly, it's only it was maybe a foot difference. This USB cable was able to communicate just fine through this power back to my computer, and I would attribute it to the active hub making sure that the signal is strong and clean. So at any rate, it doesn't bother me. I am not leveraging any of the additional USB 2 ports at this time, and I still get all of the benefits of the distribution system that the mount offers, because I'm able to take advantage of the ports in the saddle. So, and including the USB 3. So that allows me to keep a very tight set of, well, these are not yet the final cables, but it does allow for a very tight, neat cabling setup between your image train, your imaging equipment and accessories, and your saddle. And once this is tightened up, there will be no opportunity for cable snags as the mount slews. So this is a very important principle, and in terms of design, and it's quite effective. Okay, so that's data. In terms of power, I do have two power bricks. One of them is the standard, the Rosneck 12 volt 5 amp power brick supplied by iOptron, and then I happen to have had a 12 volt 8 amp power brick that I've decided to use in my initial testing. Both of these power cables come up. One is feeding the mount control board, which is the iOptron cable, and then the second I carry up into the 10 amp DC input on the CMS system. This power then comes up and feeds two of the DC outs on the saddle on this side. Now, just a reminder, there are also two DC 12 volt 1 amp outputs on the right hand side of the saddle, and again that is fed from the power that is being fed into the main controller. So that's power, and again I separate my power cables from my data cables. No need to introduce any noise, and I neatly attach all of this with Velcro. You can see the hand controller is attached with Velcro. My GPS antenna is connected with Velcro. The USB hub Velcro, and even the power bricks Velcro. And this inexpensive power plug is connected with Velcro. I like it because it keeps it tight enough for me, and as long as cables don't interfere with each other, and that while the mount is slewing, I don't have cables tangling up and affecting guiding, I am very, very pleased. So overall, it's neat. Yes, I will I will take some time to clean up some of these and get shorter USB cables. But for purposes of moving forward with first light, I don't see any reason why I didn't see any reason why I had to wait. Okay, I realize that there's filming from the observatory has its disadvantages. It's a tight space and often dark and difficult to see all the things that I'm showing. But I wanted to just put on paper for folks who are interested the exact data connections that I use between the imaging train, the mount, and the observatory systems. And I'll go from observatory systems back. For purposes of this explanation, the mini PC, the USB 2.0 hub, and the switch I would consider observatory infrastructure. So the mini PC obviously connects to the main control board of the CEM120 via an Ethernet connection, which is facilitated with a very simple switch. The data connections between the mini PC and the cable management system input on the CEM120 are via the USB cables, only noting that for the USB 2.0 connection, the 15-foot distance was a push, so I do have an active powered USB 2.0 hub in between the two. Okay, so if we move over to the imaging train now, obviously there's a main OTA and a guide scope, and they both have imaging cameras attached to them. In the case of the main OTA, there's an ASI 1600 monochrome pro camera, which via a short USB connector connects to the CMS output in the saddle of the CEM 120. And because the ASI 1600 and many of these Astro cameras have their own hubs built in, I'm able to connect the accessories that are used in conjunction with that camera directly to the ASI 1600 via USB 2 connectors. So the filter wheel and the focuser are directly connected to the ASI 1600 via short USB cables. And in fact, they get their power from those USB cables. Now, the guide scope is connected to an ASI 120 mini. It's a monochrome camera, and it has its own USB 2.0 connection to the saddle. And I like to separate the two different image data channels into their own USB connections. So at any rate, hopefully this illustration makes it clear. I didn't go into power connections, but it's safe to say the ASI 1600 has a barrel connector which connects to power off of the saddle. I use one of the 5 amp outputs on the saddle. I've read documentation that suggests you can power that camera off of the 1 amp outputs of the saddle. I wouldn't do that. I prefer to ensure that there's sufficient power to the camera. And then if you have dew heaters, I happen to use dew heaters as well. I use a dew heater for my guide scope. It's a USB based dew heater, so I power that off of one of the USB 2.0 ports of the saddle. And then on the main OTA, I currently have a dew ring from Celestron, which has a barrel connector that I have tested using the another 5 amp output off of the saddle. So at any rate, but hopefully this clarifies things for folks. Okay, for those of you who are going to connect the mount and your observatory computer via an Ethernet connection, there is some configuration that you need to do using the hand controller. The IP address of the mount needs to be obtained and noted, because you will need to specify that IP address when Commander launches, and you have to specify the IP address for Commander to connect to your mount. So under settings, there's an option for there's an option called Network Options. You'll select Network Options, and with Network Options, you'll see another submenu, which includes status of your wired, status of your wireless networks, and some options to manually refresh or restart or restore to factory. If you go to the wired status, you'll notice that it's trying to reconnect. It'll say reconnecting, and it won't be able to connect the first time. So go back and choose manual refresh. Manual refresh will obtain an IP address for your mount. There's just a warning that it's going to terminate any connections that may exist. Once it reconnects, you can go back and go to wired status, and you will now see the IP address associated with your mount, and note that it is on port 8080. You'll need to specify that IP address and that port value when connecting to your mount via Commander. From that point forward, it will remember it so long as your mount remains powered and your network remains powered. Okay, so why don't we go ahead? I have a remote desktop connection to the observatory system. Let's go ahead and connect using the Commander software. It's already connected using the IP address. Because I've already connected on the IP address that it was refreshed with, it automatically detected the mount. And of course, I can open up the mount panel. For those who are interested, I am using iOptron Commander 9.07, which I think is the latest version of Commander. I'll also note that I have not updated the firmware that came with the mount. I haven't even checked the version of the firmware yet. And I do that intentionally because I do not want to get firmware fever. The rule of thumb, as published by iOptron, is if your mount is working, do not upgrade the firmware. There's no need to upgrade the firmware. So until I get to a point where I feel like perhaps there's misbehavior, then I will look at the firmware, and I will look to see whether or not a firmware is a solution to any problem that may present itself in the future. Last thing we'll do here is we'll just launch Nina, and we'll confirm that Nina, in fact, can connect to the telescope using the Ethernet connection and the latest iOptron driver. iOptron does act as the ASCOM driver for Nina, so I'm going to go to my equipment. I'm going to select the telescope, and I have the driver, which is the iOptron has an ASCOM driver that covers a number of their mounts. This is the correct one, and I'm going to hit connect. And at this point, I am now connected to the mount, and I can Nina will have the ability to slew and control the mount. So all looks good, and with this, we officially can go take a look at first light. Okay, for me, the whole point of first light is to make sure that everything that I've done in the deployment workflow has resulted in a stable system that can capture images and then, if needed, be further tuned later on. So with that in mind, the first thing I did was a fine polar alignment. I had used SharpCap for this purpose, and the night before, I really quickly achieved a polar alignment that was within 20 arc seconds of error. And that was good enough for me to feel happy about my pier orientation and the investment I made in that base pier plate. But the fine adjustment capability of this mount is really good. So I decided to spend just another minute or so to see if I can improve on that error reading. And with just a few subtle adjustments, I was happy enough to move on with 6 arc seconds of a polar error. The next test was to make sure that the dome and mount geometry that I had calculated was correct. So I decided to slew to Fomalhaut, which happens to be visible low in the southern horizon in November. And given I hadn't done any star alignment procedures with the mount itself, I thought this might be interesting. Well, it got very close, and with just one adjustment, it was within 6 arc seconds of center. More importantly, the rig itself was really well centered with respect to the dome shutter, and that's a good sign that I won't have problems during the sequence. So I then did a quick PhD2 calibration, which looked awesome, and decided to point at triangulum just for a few exposures. And yeah, this was very nice indeed. Tracking was really good. It was guiding very well, and the subs were looking sharp. So with that, I said, let's pick a target and let this baby run free all night long and hope for the best. Okay, I chose NGC 1975, the Running Man Nebula, as the target for the first light sequence with the CEM120 mount. For one reason or another, I've been challenged by this region of the night sky during the early fall, and I thought it would be cool to put the CEM120 to the test. In terms of the deep sky sequence, I defined a set of instructions which included smart camera exposures for each the luminous, hydrogen alpha, sulfur, and oxygen channels. And these instructions called for 32-minute exposures at a gain of 139, an offset of 21, and 1x1 binning. I also specified dithering every 3 frames. I had 2 global triggers set up for the sequence, one which was to run an autofocus script after each filter change, and 2, perform a meridian flip no later than 10 minutes past transit. The guider, of course, was connected to PhD2, and which I had done a quick calibration and ran the guiding assistant for. So every the sequence is going to tap into every aspect of my image train. It would be a really nice test of all the connections and the sustainability of those connections. So I hit the start button and I went to bed. When I woke, I was really pleased to see that the sequence itself completed, and I was happy with the final sub that was captured sitting in the image view window. Now, this last sub displayed has some issues, but those are unrelated to guiding. Rather, those are some aberrations that are caused by the current state of my C8 telescope and the optics train itself. And we'll actually see we'll see more evidence of that in a little bit as we dig into the subs that were captured during the 4-hour sequence. Okay, so here we are in Cyril, and we're going to get a better appreciation for the quality of the guiding by looking at the subs directly. And I'm just going to flip through the hydrogen alpha data just to get a sense for the quality of the guiding. This is the first sub that was taken, and these are uncalibrated, so you'll notice there's some amp glow in the corners, and you might even be able to pick up on some dust motes and things like that. But as I kind of flip through this, taking a look at the stars themselves, the stars are pretty good. They're looking far. They don't look bloated. I know that I have some issues with collimation on this scope that I can improve, and I am using this dew ring heater, which I do think is creating some thermal gradients. But overall, these stars look they look about as I would expect them to look, I should say, given the optical tube assembly that I'm using here. Remember, I chose something that I'm familiar with, so that I can not be troubleshooting 2 issues at once. But this looks pretty good. These are consistent, clean, and this is an hour's worth of exposures for HA. So I'm going to go ahead and I'm going to process all the subs across all the channels, and let's see if we can't create ourselves a few stacked masters. Okay, so this is why it's always important to go through your subs. I got done stacking HA, sulfur, and oxygen data, and those stacks look pretty good. I'll show you that in a moment. But I went ahead and I started looking at the luminous data, which I wanted to take a look at, particularly to see whether or not I could tell when I started to have the more severe aberrations on the stars. And lo and behold, as we go through and reach about eighth and then ninth sub-exposure in the 30 exposure part of the luminous sequence. As soon as I hit the actually this would be the 11th exposure. It's the last time that we were in the original orientation. There was a meridian flip that took place. And meridian flip, the very first, there's a couple things happening here. One, guiding did not settle, or the scope did not settle. So the 12th exposure is a throwaway. Let's in fact get rid of that. 13th exposure guiding has seemed to have stabilized itself, but we have these significant spikes in the stars, which could be a culmination issue that has occurred here with the mirror flip. It's hard to say, but certainly from here on out, we notice that our stars are. We have some serious aberrations in the stars, and we can associate it with the meridian flip. I had noticed one other frame in here earlier. I'm going to see if it's still visible. I think that was already found. Okay, there. This is the other frame. I just want to get rid of this because obviously we have a artificial streak through here, potentially aliens. Okay, with that, the question becomes: do we leave these subs with these aberrations in? I happen to like spikes, so it's sad to say I know it's a sign of poor optical condition or some abnormal condition in the optical train. But I like stars, and we're doing this because we like this stuff. So I'm going to go ahead and calibrate this sequence here. Might as well show you. I have software that I have written that helps me to do this efficiently, and let me just go ahead and calibrate these frames. And I'd like to see how well Nina registers, goes through the registration process when you have a meridian flip. And by the way, isn't it great news that the CEM120 was able to handle the meridian flip with the settings that I had? That is fantastic. So let's go ahead and register all these and see what happens if Nina's able to do all the heavy-duty rotations. Yeah, I know. Luminous, filter on big young stars near us. It's going to feel a little bit bloated here. But let's see how this registers up, and then we'll go ahead and give it a stack just to see what the stacked image looks like here. So I save my stacks in a workspace that my software creates, but hold on, stacks. And this is going to be Luminous Master. So let's go ahead and start stacking. We'll take a look at the luminous stack, and then we'll get a closer look at all three stacks that this thing produced afterwards. Okay, so meridian flip is obviously, you can already see that we're going to have a reduced field of view here, which is quite all right. I don't mind this tightened field of view. This is going to actually be a beautiful image when we're done, so stay tuned. Okay, here we are in PixInsight, and what I've done is taken the masters that were created within Serial, the master stacks of each of the 4 channels that we did in our sequence, and I simply registered those against each other and did a dynamic crop. And yeah, we've lost a little bit of field of view due to the meridian flip, but that's quite all right. and I've thrown a screen transfer function on each of these. And I have to tell you, I'm overall, I'm really excited about this image, and I think there's some wonderful levels of detail in the HA that are going to be pulled out real nicely. And I think the luminance stack is going to provide us with a lot of punch. And both the O3 and the S2 data look good as well. I do notice some interesting optical aberrations around the stars. This is largely an issue that I have with the C8 right now, and this has absolutely nothing to do with the 120. Very nice set of stacks. Okay, everyone, I'm going to call that a wrap for this long video. I think we can safely conclude that the CEM120 did its job. We did our job. We made sure to follow a methodical approach for deploying this this expensive mount. And I look forward to the remaining journeys that we have with it, as well as other content on the channel. So if you haven't already done so, go ahead, subscribe, and that way you'll get notifications when I'm putting out new content. In the meantime, thanks so much for watching, and I'll see you at the next video.